What's up, guys? Welcome to episode 8 of the BERT research series. We've got plenty more BERT-related content ahead of us, but this is going to be the last episode of the BERT research series where we're looking at the inner workings, making sense of the architecture, and looking at how BERT does what it does. So for this last episode, I want to look at the pre-training tasks that Google trained BERT on. And those are the masked language model and next sentence prediction. So we looked briefly at those back in episode 4, but there's more detail that we can go into. And I think it shows you a lot about how BERT is actually able to learn such sophisticated things about language in general. And then I thought it'd be fun to look at the difference between OpenAI's GPT and BERT. These two models are actually very similar. GPT came first and then BERT was kind of an improvement on it. So, now that we kind of understand BERT and we understand the dialogue around these models, I think it's fun to see the history. So I think that'll be a fun place to kind of wrap things up. So back in episode 4, I shared this slide, and when I was first learning about BERT, I'd read things like, yeah, BERT is really powerful and it's getting state-of-the-art results on all these benchmarks. So this is a really exciting model. And what it does is, you can cross out a word in a sentence and BERT will tell you what word was crossed out. Or you can give it 2 sentences and it will tell you whether those occurred consecutively in the text or whether they're not related. And those don't sound very interesting, right? Those don't sound like very useful tasks. So why is BERT so exciting if that's what it does? So of course the clarification there is that these 2 tasks are what I like to call the fake tasks. Or the real term that we use is they're pre-training tasks. So the idea is that the model is trained on these tasks, but then we actually cut out the part of the model that deals with these tasks, and we replace it with our own application that does something useful, and we reuse all of the pre-training knowledge that the model has. So even with that clarification, I think these pre-training tasks are a little funky. So I think it helps to kind of to think about what makes a good pre-training task. So first of all, it does not need to be useful. It doesn't need to have a real-world application because we're not going to use it for that, right? It's just pre-training is the purpose. And it also doesn't need to be solvable. I think that's another kind of confusing aspect of the pre-training tasks. So with the masked language model, that's a pretty hard task, right? If you were to give me a sentence where you've crossed out a word, I think I'd only be able to predict the right word, some percentage of the time. There's only so much you can infer from the context, right? So it's fine if BERT only gets the answer right 30% of the time. I don't know what the actual accuracy is on the masked language model, but really what we care about is we want it to be doing its best on the task, and we want it to be learning a good understanding of language, as a byproduct of trying to solve this potentially very difficult task. So yeah, and then what we do want for the task is that we want it to be unsupervised, right? We have very limited labeled training data versus if you can train the model on just plain text without any labels, then we have Wikipedia and the book corpus and the whole internet. We've got plenty of text. So if we can train the model just using plain text, we can then we have a much larger training set and we can train much bigger models, more powerful models. And finally, we want the task, I'm using the word, we want it to be difficult. We want it to require that the model, learn complicated things about language in order to solve the task. So If the task were too easy, then the model wouldn't, it wouldn't become very smart. So we need it to be hard. And then the final quality that BERT adds to the equation is that ideally we want the task to allow for looking at like the full context of the sentence on the input. So we'll talk about that more towards the end. But that's kind of a key aspect of what BERT accomplished. So here's what an actual training example looks like. Something that's kind of surprising is that the NSP and MLM are actually, they're trained at the same time. So I'll show you what that means. So we take two sentences. Half the time, the second sentence is randomly selected from the text, and the other half of the time, it's the actual next sentence. So here I've picked like two sentences that go that are actually consecutive, so A and B. And then we need to tokenize these sentences and add the special tokens. We add the CLS token at the beginning, and we add the SEP token in between sentence A and B. So I like to draw. Do you? Okay. And then for MLM, we do some substitutions here. And there's kind of some proportions to, like what words or how many words get substituted in what way. And there's actually like three different things they do. So the first is that they mask 12% of the tokens. So roughly 1 in every 8 tokens gets replaced by the special mask token. And then 1.5% of the tokens they take out and they replace it with a random token. And they pick the random token with a unigram distribution, meaning that the more frequent words are picked more likely. So pick the word "the" is a good example. And then finally, another 1.5% of the words aren't touched, but they're flagged for prediction, and we'll see what that means. So once we've made these modifications to the input, we send it through BERT. We send it through the 12 transformer layers. For the first token, the CLS token, we give it to a NSP classifier. So this is a set of weights which are responsible for predicting whether sentence B came after sentence A. And so the CLS token, when self-attention is happening in these transformer layers, it's going to be looking at like every other token in the input sentence in order to make, to put all the information that the CLS token needs to make that classification decision. And then the tokens that we didn't touch, their embeddings we just discard. We don't do anything with them. But the ones that we either swapped or flagged, we have a separate classifier, the MLM classifier, that has a softmax output. And so it's got a probability distribution for every word in the vocabulary. And its job is to try to predict, what's the most likely token that was here. So these guys, we don't do anything with them. And then here, this is the one where we didn't change it, but we've flagged it for prediction. So the model has to predict the original token, and the classifier or the model, like, it has no idea whether this token is the original or whether it's been randomly replaced. But we're going to make a decision. And then finally, we've got the one where we did actually swap it. So why this business here with like the swapping of tokens? Why not just do the masking on its own? Well, they show some results in the appendix of the paper where they did experiments on this and they found this ratio worked the best. And I think you could picture how the mask embedding is kind of a useless embedding. It tells the model, I don't know what this word is, right? And so the model has to basically reconstruct the word to by looking at the context, looking at the other words around the mask token. And so, I could see how, I think you could make an argument that the model might get slightly biased towards inferring the meaning of a word from its context and not relying enough on the input embedding itself. So if this were an application setting, then we wouldn't be masking any of the tokens. We'd give it all of them. And we wouldn't want the model to ignore the embedding for the word to, and just try to infer it from its context. We'd want it to leverage the input embedding for to. So they show some results. It doesn't, the difference isn't huge, but it does work better when they do this swapping. Maybe one final note on this illustration. It was kind of interesting to me to see that since the two tasks are run jointly, it means that next sentence prediction is running on damaged text, right? The sentences have been mangled a little bit by like swapping out some words for the mask token or swapping some tokens out for the wrong token. So I'm not sure how that impacts things exactly, but I thought it was interesting. So on this slide, I took some text from the Wikipedia Commons data set. I ran the BERT tokenizer on it, and then I applied their statistics to sampling the words to be masked. So this is just kind of an example to give you a feel for how masking impacts the text. Maybe the most notable thing to me is that 12% is kind of a lot. There's a lot of mangled tokens here, all right next to each other. Also, the swapping is done after tokenization, so it's quite possible that the swap token would be a subword. It could be like in the middle of a word. As far as like the steps involved in the weight updates, I'm not sure the exact details. This is kind of what they say about the loss. The training loss is the sum of the average MLM likelihood and the average NSP likelihood. So I don't know whether that means that they calculate the gradients for each of those predictions and then sum them together or average them before making the update, or whether they're done one at a time. So not sure there. One thing that was very interesting, though, that I feel like I haven't seen this mentioned anywhere else, and it seems kind of significant. So they say that to generate each training input sequence, we sample 2 spans of text from the corpus, which we refer to as sentences, even though they are typically much longer than single sentences, but can also be shorter. So what they're saying there, I think, is that they're not actually looking for sentences and sentence boundaries. They're just taking random stretches of text and using that, as the segment A and segment B. And, they say they are sampled such that the combined length is less than or equal to 512 tokens. So BERT has that maximum input length. And in order to feed it 2 sentences together with the special tokens, it all needs to be less than 512. It doesn't really say in here what their sampling strategy is. I'd be kind of curious to see is the length uniformly random, or how do they decide how much text to take? But yeah, I think that means too that next sentence prediction, it's almost a misleading title, because it's really more like you could take, it sounds like from the way they're describing it, that I could take this piece of text and call that sentence A, and then this piece of text and call that sentence B. So it could be that the separation occurs in the middle of a sentence. I think I'd be curious to see if I'm wrong about that, but I think that's what's implied here by their description. How does BERT know which tokens belong to the first sentence versus the second sentence? It seems obvious in these illustrations because we've kind of laid them all out and separated them. BERT doesn't have that information though. So the way that's communicated to BERT is actually with these segment embeddings. So at the very bottom layer, layer 1 of BERT, the input is actually comprised of, for each token, we look up its embedding in the vocabulary in the word piece model. So that's like a vector of length 768. And then there's two segment embeddings, one for segment A and another for segment B. And depending on which sentence it is, we just add that to the embedding for the token. And just a small detail, like CLS and SEP both get the A segment. And then we looked at this in the last episode. There's a unique position embedding for every input position, and that's added in as well. So these three things are summed together before, and that's how we construct the embedding. That's the actual input to BERT. And yeah, and then one interesting thing that I didn't know when I recorded the last episode is that whereas the original transformer used those two sine and cosine equations to generate these hard-coded position embeddings, they imply in the BERT paper that they actually learned the position embeddings. And then they also learned the segment embeddings as well. So I'll show you the part of the paper where that was. Yeah, they kind of refer to it in this interesting detail here. So a challenge with BERT is that the longer your sentences are, the longer your input text, the longer it takes to run BERT, and that's because it's quadratic. So for every input word, you've got to multiply its query vector against every other key vector. So it's n squared with the sequence length. So to speed up their pre-training, they first pre-train the model with a maximum sequence length of 128 for 90% of the steps. So they do most of it with a smaller sequence length, but then they do the last 10% with a sequence length of 512 to learn the positional embeddings. So they're that pretty clearly implies that the position embeddings are learned, not hard-coded. So to wrap things up here, I wanted to share some of the history of BERT. I think it's really interesting to see kind of how BERT came about, and I think you'll find it pretty fascinating too. So before BERT, there was a model called the OpenAI GPT. It stands for Generative Pre-training, and they had this great idea. They decided to take the original transformer and strip off the decoders and just use the encoders, and then scale it up. They took it from the original transformer 6 layers, they took it up to 12 layers, and they increased the embedding size from 512 to 768. And then they pre-trained it on a big unsupervised learning task on a ton of text, and then they applied that to a bunch of NLP benchmarks and fine-tuned it on those benchmarks and got really impressive results. So you should be thinking to yourself, like, wait a minute, that sounds exactly like BERT. And it is. It's very, very close to BERT. So here's kind of where the difference came in. So in order to apply this great idea of unsupervised pre-training, they need a pre-training task, right? And the standard one that everyone used was called language modeling. It's where you have a sequence of words and you're trying to predict the next word in the sentence based on the previous ones. So the problem with that task is that with the original transformer, with the self-attention mechanism, it gets to look at the entire sentence, right? And what that does with the language modeling task is it allows the model to kind of cheat. So let's say we mask out the word pre-training and in the sentence, and we give it the other words, differences in model architectures. And we train it, to predict pre-training. And then the next training sample, we mask out the word model and give it the other words, differences in pre-training architectures. The problem is we just gave it the word model, as an input in the previous training example. So I'm not sure the exact mechanics, but somehow the model is able to use that information to kind of cheat at the task, and it doesn't learn language as well. So that meant that in order to use the language modeling task, they had to restrict the self-attention to only look at the previous words in the sentence. So to predict, if you mask out pre-training and we're trying to predict that word, then self-attention only gets to look at these two words. We don't give it the later words in the sentence. So that's so the masked language model, in contrast, right? We might mask the word pre-training, and that means the model never sees that word. So that's kind of the big difference there. There's a great interview on YouTube with Jacob Devlin, who's the first author on the BERT paper. And it's between him and a woman from Kaggle. I'll put the link down in the description. And it offers some interesting insight into kind of like how he came up with BERT. So he was actually working on applying the masked language model approach to the transformer, but kind of at the original scale of the transformer. And he says that when the OpenAI paper came out, when GPT came out, he said it was kind of absurd how good the results were just from training a big language model. So he did some ablation studies, which just means like taking out different pieces of the model to see maybe what the most important aspect of it is. And it kind of showed that the key was just that it was really big, that it had 12 layers and larger embeddings. So he tried upping the scale of his masked language model, and it worked really well, obviously. And so it seems like, all right, so then it was really genius to apply the MLM technique. And he has some interesting stuff to share there too. So the masked language technique has been around a long time. It's called the close task, and it's been used by educators to assess a child's reading level, see if they can predict like what the missing word is. So he says that the MLM idea was actually kind of obvious, and that other people have applied it before to NLP. But here's kind of like the difficulty with it that he thinks maybe has prevented people from going with this idea earlier. So the nice thing about the standard language model is that you get to predict every word in the training text, right? Because you're just going through them one at a time. So the number of training samples that you get out of the text is equal to the number of words in the text. And if you're doing MLM and you're only masking, like 1 in 7 words, then it's not clear like how much longer you're going to have to train the model in order to get good results. So it could be, as much as like 7 times as long. But they found out that it's actually more like 20 or 30% longer, not 7 times. So, yeah, so his kind of conclusion is like, people just hadn't tried it at scale, and that was kind of the key. So pretty interesting to see kind of how that all came together. So that's the end of the BERT research series. Thank you guys for sticking with it. I know it's been a long journey. I'll probably go back to episode 7 at some point and publish kind of a part 2 where I'll cover residuals and the layer normalization. But yeah, we've got more application-oriented BERT content on the way. We'll probably also look at some more BERT variants. So I'm excited to dig into more topics with you guys. Thank you.